Once again, welcoming you all to the physics class, dear students. So, on the previous classes, we were discussed about the interference. Then, after types of interference, that is constructive and destructive, and on what pattern they are conducting the experiments. And then, after we discussed the YDSC, Young's double slit experiment. Then, after thin films, interference in thin films. Okay, so and related problems, we have completed all this. We are entering into the next property that is called as diffraction. What do you mean by the word diffraction and where we are observing this diffraction? So diffraction is a phenomena in which light spreads. Okay, so whenever bending of light into the encroachment is called as diffraction. So simple words, bending of light ray, I mean the light is deviating from its rectilinear propagation is called as what guys? Diffraction. So we want in a very simple explanation. Okay, so guys, first of all, think that this is an obstacle. This is what Nana obstacle, and here we are having a very big screen. Okay, now we are having very big screen like this. Now when a light fall on it, so in general, when light is obtaining from a point source, light will create a shadow like this. Is it right? So here this is completely dark. And the remaining surfaces will be bright. That is, it cast, I mean these objects shadow is casted here. Is it right? So first, once again, this is a source of light and this is an obstacle. This is a source, point source, and this is an obstacle. Okay, and this is a screen. It casts a shadow. Now whenever it is casting a shadow, if the wavelength is comparable with the size, I mean d is the size of the object like this. Okay, now if this wavelength is comparable with the size of the particle, now actually here if you clearly observe that these two are following which rectilinear propagation, but when this is comparable, at that situation light will undergo like this, and it will form a small. Okay, I mean it will create alternate bright and dark bands. This formation of alternate bright and dark bands or bending of light rays is called as diffraction, or spreading of light into its encroachment. Encroachment is nothing but what, guys? So into the shadow region, into the shadows. Actually this is the region, but it creates a black spot, a slightly black spot here. Okay, this type of spreading is called as diffraction. Okay guys, hope you understood about the diffraction. It's a very, very, very simple phenomena, guys. So bending of light ray, when it meets an obstacle of its size, I mean simply deviating from its rectilinear propagation, away from its rectilinear propagation. What is rectilinear propagation? Moves in straight line. See, actually the light has to move straight away like this, but it is changing its path. Here also it has to move, but it's changing its path. This change in its path is called as diffraction. I mean, due to this change in here, it created some pattern. This pattern is called as what, guys? Diffraction. Okay, now I'm going to give you a very clear idea how this diffraction, and here diffraction is of two types, guys. One is a Fresnel and one is a Fraunhofer. Okay, so what is this Fresnel diffraction? What is this Fraunhofer diffraction? Okay, first of all, we will discuss the diffraction very, very clearly. Okay, with respect to the experiments, then we will go ahead. Okay. Okay, so just, yes guys, so we will discuss that. Okay, just a moment. Okay, so yes. Okay, so before we are entering into the main topic, so we will just go through the topics here, then we will go ahead. Fine. Yeah. Okay, so it is a phenomena of bending of light around the corners of an obstacle or aperture of the size of the wavelength of the light. See, this is a, I mean, I already just explained. Na? So here, instead of this light ray, it has bended slightly. This bending of light around the corners of the obstacle is called as what, guys? Diffraction. Diffraction is the characteristics of all the waves. I mean, whether it is a sound wave, whether it is a water wave, whether it's a mechanical wave. So all the waves will exhibit diffraction. Greater the wavelength. So main point you should keep in mind. Greater the wavelength, higher will be the degree of diffraction. So for diffraction for radio waves as well as sound waves will be more when compared to the light, because higher the wavelength for radio waves as well as the sound waves, the wavelength is very higher. So a diffraction effect will be very high in sound as well as for radio waves. So you need to keep in mind, greater the wavelength of wave, higher will be its degree of diffraction. Experimental study of diffraction was extended by Newton as well as Young, and most of the systematic study carried out by Huygens on his basis of wave theory. So here the experiment is, I mean, so many experiments were conducted. In that first it is extended by Newton. Okay, so Newton explained first this one, then after Thomas Young. But Huygens has carried out more uh, more study on this diffraction of light. Okay, guys. Now the minimum distance. Okay, so here the minimum distance at which observers should be found the obstacle to observe diffraction of light of wavelength lambda around the obstacle of size d. See, what is the minimum distance between the observer and the obstacle? See, for example, just now we discussed it. Is it right? So just now we can observe. I am drawing here. You can check here. So, guys. So I already said that. Okay. Now this is a point source and this is an obstacle, and it is the cast. It is producing a diffraction pattern. Is it right? Now here the diffraction pattern it is producing. Now what is the minimum distance from the obstacle? What is the minimum distance? I mean, here is an observer. Okay, so what is the minimum distance between the obstacle and the observer in order to observe the diffraction? That is x is equal to t square by 4 lambda. If the distance is of this range, then only a person can observe the diffraction. Otherwise we are unable to uh, observe the diffraction. So where d is the size of the obstacle. Here this is called as size of the particle. Lambda you already know, wavelength of the particle. Okay, should be from the obstacle to observe diffraction is how much, guys? D square by 4 lambda. Okay, now coming to the point here, we are going to discuss. We are having, I already said, na, the total diffraction is classified into how many types? Two types. One is Fresnel and one is Fraunhofer. In Fresnel diffraction, the screen and the source are at infinity distance from the diffracting devices. Okay, so sorry, are at finite. Okay, now if the screen and source at finite distances from the diffracting device or the obstacle, it is called as what? Fresnel type. Okay, it does not require any special varieties. Okay, like it does not require any special varieties for uh, producing this diffraction pattern. Okay, so directly it will be observable. So you need to, in Fresnel diffraction, the only concept is what? The screen. obstacle or at a finite distance. Okay, so you can, I'm showing you. Okay guys, okay, you can able to see guys. So here this is, okay, it is a source, okay, here is the screen, okay, and these are separated by a distance of capital D. Now the whatever the light it is there, and this light will spread, which will produce a diffraction effect. Now the distance here it is finite, and I mean this is known and this is also known. Okay, this type of diffraction is called as Fresnel diffraction. So either source or screen or both are at finite distance from the diffracting device. So this is nothing but diffracting device. This small hole will act like an obstacle. Okay, its small hole or small slit will act like a obstacle. Okay, so here we are the obstacles may be a straight edge, narrow wire, small opaque disc. So what are the different common examples we can consider? Straight edge. Okay, now coming to the next, narrow wire as well as small opaque disc. These all are the common examples for the Fresnel type of diffraction. Sir, we want to still more clarity, sir. For example, guys, here I'm going to yeah, I think you already learned in your very small classes about this point. Okay, so bending of a light, I mean so here this is a still water and the disturbance is produced, and disturbance, due to these disturbances, so the light will start moving circularly like this. Okay, now if you keep a straight edge here, okay, actually it should cut off this, but from here onwards the light will continues like this. So actually from here onwards the light is the water waves will still continue. So this continuation is called as, this how the water waves are bending. Similarly light wave will also bend, and this bending of light wave is called as what, guys? Diffraction. Okay, now coming to the next, Fraunhofer. See, the Fraunhofer diffraction is a similar type, is also similarly, but the source and screen are effectively at infinite distances. See, if the source and the screen are at infinite distances from the diffracting devices, it is called as Fraunhofer diffraction. Okay, in that we use lenses. In Fresnel diffraction, we are not using any, convex lenses. Okay, but in Fraunhofer diffraction we are using convex lenses in order to obtain diffraction pattern. Okay, these are the two types of diffraction. In both the things the experiment is common. The only change is in Fresnel the sources are at finite distances. In Fraunhofer the source and screen are at infinite distances. And in Fresnel we are not using any convex lenses. In Fraunhofer we are using convex lenses. Only these are the things, and remaining all are same for those. Now I already just said, now we will observe practically. You can see, able to see right now. So this is what our diffraction pattern is. Yeah. So you can see. Here this is a obstacle and this is our screen. Okay. Now I'm just I'm owning the source. You can able to see this is the center one is a very dark one. Okay, the topmost one is a topmost is bright, alternate dark and bright bands. Here what we are getting, guys, alternate dark and bright bands. This alternate dark and bright bands we will call it as what, guys? Diffraction. But sir, in interference also we observed the similar manner. In interference, it was caused due to the two waves superimposing each other which are in same phase. But here this is observed due to the combination or superposition of secondary wavelets of same light. Superposition of secondary wavelets of same waves. Okay, so you can see for different patterns how will be. Yeah, this is the pattern for a square. If you use a square obstacle here, you can see the square obstacle. If we use a square obstacle, we are getting the pattern like this. If you use square and a circle like this, we are getting that. So if you clearly observe that, we can't actually this circle and this square are at a single point. No, they both were separated by a certain distance. But you can observe that the diffraction pattern, it is the combination of circle and square. So this, I mean, the light falling, I mean, light which coming from the circle and light coming from this square, both are coinciding at one single point. Can I able to check here? Okay. Now if I width the square width, I increase the square width, we are getting different pattern. Now increase the circular, we are getting different pattern. Reduce it. So if you clearly observe, guys, smaller the obstacle, fringe width will be more. Smaller the obstacle, the fringe width or central maxima will be more. If the if the obstacle is big, the central maxima or fringes are very small. You can observe that for circle it is very small, is it right? The size of the obstacle of the circle is very small, but here the shape of the maxima for the circle is big, and the size of the obstacle of the square is very big, but the central maxima for the square it is become very small. But when I reduced here, we are getting both are big. For different things, I will show you right now. This is his pattern. Okay. Now, so many stars, I mean, so many holes are there at that time. Okay, if the spacing, when I changes the spacer, this is all diffraction. If you clearly observe that, we are obtaining once again circular pattern. Once again, circular pattern is obtaining when the these multiple obstacles were separated by a larger distances. I mean, distance between the obstacles is very small, the pattern will be big, and when the distance is very high, the pattern is small. Opposite. This is called as diffraction. Okay, and diffraction will be different for different wavelengths. It mainly depends upon the wavelength. Okay, you can check. For different wavelengths, it will have in different. Yeah, you can observe very clearly for diameter of a smaller hole. Okay, eccentricity is nothing but position. I mean, we are using circular, narrow like that. So this is a narrow slit. I mean, parabola, hyperbola is there. None. So actually, this is an ellipse. If we use ellipse, we are getting the diffraction pattern like that. Okay, I mean, it behaves like a slit. Okay, I mean single slit. Okay, fine. Now we use a eccentric 0 only. That is the circular point. Now when small circle, I mean obstacle is very small, you can check here, the maxima is very small here. Okay, but when as I'm going, I mean as I'm increasing the wavelength, the size of the central maxima is also getting increases. So the fringe width or the central maxima is directly proportional to the wavelength. Higher the wavelength, higher will be the maxima. Higher the wavelength, higher will be the width. Okay, this is what you need to observe it very clearly, guys. Okay, questions will be there. If we replace with the blue light with the red light, what will happen to the central maxima? So what will happen? The central maxima will increases. The size of the central maxima increases. Okay, that point only. So if the yellow light is replaced with the blue light, so what happens? The central fringe decreases. Those all the topic type of questions may appear in your exam. Clear, guys? Hope you all understood. Okay, and for so you can observe some. We will do some magic here. Yeah. So this is the size of a particle like a person. Okay, and diffraction pattern for this person will appear like this. And when we rotate here, it will be create certain effect like this. Guys. Okay. So if I increase the obstacle too much, the fringe pattern will be once again forms as a circular paths, alternative circular bright and dark bands. And you can see the size of the central maxima decreases. But when I make the obstacle smaller, we can able to see the fringes or central maxima as very big. Okay, so this is what we discussing about the diffraction. What is this diffraction? Bending of a light ray. So you can observe here, actually due to this bending, so why this we are getting alternate dark and bright bands. Of course I will explain through the formula, so at that time you will get a clear idea. Okay, so here guys, very simple logic, very simple logic. Okay, so that I will tell you soon, and once again observe it clearly. Whenever, so essentially when we use it will act like a single slit. Of course we don't have the graph here, but when we draw a graph for this, when we draw a graph for this pattern, okay, you can observe that actually we are having an experiment. You can observe that the central one is very, I mean it is much intensified, and whereas the besides one is less intensified. Okay, so if you draw the graph here, okay guys, this will be like this. Okay, okay, so this is how the diffraction pattern will be. Okay, now this one is called as central maxima. This is a central maxima. Okay, first order maxima, second order maxima. If you clearly observe that for interference we are obtaining what we are obtaining, guys, all are up and I mean straight edges like this. Okay, so what is this straight edges? Central maxima, it's first order minima, so this is CM. Okay, first minima, first maxima, and first minima, first maxima. Sir, for diffraction minima won't be? Yeah, it will be. This is a first minima. Here also first minima. Here first maxima. But as we move to the edges, intensity will decreases. Okay, so this is a central maxima. The intensity is very high. Okay, first minima intensity is very less, and the first maxima intensity is relatively less when compared to the first maxima or central maxima. Okay, so this is how the graph for the diffraction takes place. Hope you are understood, guys. Okay, now we will go to the further more topic. Okay, so hope you understood this topic. Okay, fine. Okay guys, now coming to the next, hope you all understood about the experimentation. Okay, and now we will go to the next topic. Okay, I hope you all understood clearly about the what is diffraction. Okay, here diffraction of light in a at a single slit. Okay, I already said now we are obtaining the graph for the I mean the graph for the yeah, the graph for the diffraction will be obtained like this. You can see this is what the pattern or diffraction pattern for a single slit. Okay, what is this diffraction of light at a single slit? Okay guys, here the concept is very simple guys. Okay, what is this concept that we will discuss right now? Okay, if it is a little bit more, it will be much more best. And okay, but of course, but you can able to check here. I hope it is very simple logic here. Okay, now we already done the YDSE, Young's double slit experiment. In that Young's double slit experiment, one of the slit is closed. When one of the slit is closed, the experimentation will becomes like this. Is it right, guys? So this is our screen. Okay. Now, yeah, and this light, when the size, when the see, when this D, so this is, for example, the distance is what D. If D, I mean, if D is greater than lambda, what will happen? Light will go straight away like this. Okay. If D is approximately equal to lambda, if D is approximately equals to lambda, if D is approximately equals to lambda, then light will spread slowly like this. Okay, now if D is less than lambda, if D is less than lambda, then light will spread completely like this. Okay, this spreading of light is called as diffraction. Okay, okay guys, now coming to the next point here. So what is the formula for obtaining the diffraction? I mean, what is the formula for obtaining the central maxima? That all we will discuss. Now here I'm going to give a very simple logic. It's a very simple logic. Okay, so of course we no need to derive the formula for this here, and we're not getting the proper derivation also. Okay, now guys, I'm going to explain the formula very simply how it is. I'm just telling the idea. We don't require the how formula is derived. We don't require. So, but I'm just in order to have a clear view only, I'm just explaining. Okay, now, okay, guys. Now here, this is our midpoint. Okay, now the light rays are moving here like this. Okay, now if you clearly observe, guys. Okay, now this point, whenever this is a screen, at this point we are getting what? Central maxima. Now at one single point here also we are getting central maxima, 2 points. So here wherever the region, I mean this is one part, I mean the rays which are coming directly, and these are at a particular angle. Now here, what is the extra distance traveled? What is the extra distance traveled? This is the extra distance traveled or not? Okay, initial, this angle is what, guys? Theta. If this is theta, this is also theta, this is also theta, and this is also theta. Okay, I'm telling you the very simple. Here in YDSC, we are not considering the middle line. Of course, we considered that is like a approximation here also. But here, if you clearly observe that this point is, I'm considering the central maxima C. Now here the phase difference, we are getting a central maxima, the phase difference is 0 here. Here also, I mean here the light is coming, here also light coming, so the here also the phase difference should be 0. How it will be, should be 0? So I'm adding, it is I mean it is should have a path difference of lambda by 2, and here it is lambda. Okay, so if you clearly observe that with respect to here, I mean if you consider here, so this will be how much, guys? We can consider this will be, this total will be the total path difference. Now, so here from the center point, if you consider from center point, this is the C point now. So in order to obtain central maxima, the extra distance covered is A. Extra distance covered is, you can see this is the distance. Okay, A, and A is equal to D sine theta. Okay, so here this D sine theta, this C sine theta is equal to n lambda for minimum. Okay, so why minimum, guys? You can see whenever light travels from this point, okay, you need to consider this. At this point we are getting a maxima, that is with respect to above and below we are having maxima. So how much angle they are differed by? How much angle they are differed by? Lambda by 2. Okay, you can see lambda by 2. Here it is how much? Lambda by 2. Here it is lambda by 2. Okay. So other than, I mean, for minimum. Okay. Okay. Yeah. First we will write maxima, then we will go. So if the two waves were differ by, I mean, for maxima, okay, if two waves were differ by, so what is, I mean, how much this path difference? This is a path difference. We can write here A, or we can write it as delta x. Delta x is equal to integral multiple 2n minus 1 lambda by 2. That is, we can write here d sine theta. D sine theta is equal to 2n minus 1 lambda by 2. Okay, d sine theta is equal to 2n minus lambda by 2. For what, guys? Or 2n minus 1, or we can write it as plus 1. Okay, plus 1 is more best because we are adding up. I mean, if we consider from here, it is getting only added. Always it added. So it is 2n plus 1 lambda by 2. Okay, so this 2n plus lambda by 2 is equal to d sine theta. So this is the condition for maxima. For minima, whenever they are in phase, okay, whenever they are in a out of phase, it is getting maxima, and whenever they are in phase, we are getting minima. That is delta x is equal to n lambda. That is d sine theta is equal to n lambda for minima. So here the logic is very simple, guys. What is that logic, guys? What is that logic? If delta x is equal to 2n plus 1 lambda by 2, we are getting maxima. And if delta x is equal to n lambda, we are getting minima. So we don't require the derivation here. It is too much lengthy and very big, not required to us. Even in your textbook, CBSE textbooks also, they're not given, guys. So no need. Okay. But just giving an overview and explaining that. The formula is only important. It is an opposite to the YDSC. It is opposite to the YDSC, guys. So in YDSC, we are getting n lambda. N lambda is equal to what, guys? N lambda for maxima, and 2n minus 1 by lambda by 2 for minima. Okay. Now here, but it is quite opposite for that. Okay. So this is how the diffraction for a diffraction of light for a single slit we can explain. Okay. Now here we can write here d sine theta is equal to n lambda. Yeah. From this we can write sine theta is equal to n lambda by d, and sine theta is equal to 2n plus 1 lambda by 2d. Those all are the formulas. Okay. Yeah. I hope you all understood. Okay. So these are the simple basic formulas only. No much big problems from this diffraction topic. Yeah. Okay, guys. So now one more important topic here. What is the difference between interference and diffraction? Okay. So here, interference, I mean, it's a comparison study. Actually, there is no satisfactory explanation for the comparison between interference and diffraction, but we need to talk about that. That's the reason we are just having a cross check on the topic interference and diffraction, guys. Okay, now first of all, results due to superposition of waves from two coherent sources. Okay, and diffraction is obtained results due to the superposition of wavelets from different parts of same wavefront. I already said na, single coherent source. Is it right? So in the interferences, if two waves superimpose, it will give rise to, I mean, interference will appear. But in diffraction, the same part of the wave will undergo superposition. Okay, guys. So the same part, same wavefront will undergo superposition. Okay, all the fringes have the same width. That is beta is equal to lambda d by d. All the secondary fringes are of same width, but the central maxima is double the width. So for the central maxima, it will have the double the width. How much, guys? It is 2 beta, that is 2 lambda d by d. Okay, so they might be asked the questions from this topic. I mean, from this question, what is the size of the fringe? What is the size of the fringe width for the central maxima? If one of the source in the YDSC closed, it is twice the what, guys? Twice the fringe width of YDSC. Okay, now coming to the next, all fringes are same intensity. Intensity decreases as the order of maxima increases. See, for first order, second order, third order, fourth order, and so on, all the fringes are having the same intensity, whereas for diffraction, intensity decreases. I mean, if first order, intensity decreases, second order, intensity decreases, and still on decreases. Okay, now intensity of all minima may be 0. Intensity of minima is not 0. I already said now, it is not completely 0. Okay, and position of maxima, xn is equal to n lambda d by d, and xn is equal to 2n minus 1 lambda d by d. And here xn is equal to, I mean, they will get interchange, 2n plus 1 lambda d by d, and xn is equal to n lambda d by d. So path difference is delta is equal to 2n lambda, and here for a secondary maxima 2n plus 1 lambda by 2. And path difference here for path difference for nth minima is delta is equal to 2n minus 1 lambda, and path difference here is n lambda. So it is simply quite opposite to the, what, guys? Interference. Okay, so this is what the simple explanation for comparison of interference and diffraction. Okay, so now coming to the next, diffraction of optical instruments, guys. Actually, it is very, very important in optical instruments. Now, whenever you look the obstacles through the instruments like telescope or microscope, they won't resolve the objects perfectly. Okay, what do you mean by the word resolving of the object? To show, I mean, the minimum distance between the two objects to show them distinctly is called as resolving limit. Okay, so I will see, I mean, whenever I'm seeing here, so two objects are at far away distance. If both the objects are at infinity, both will appear as a single object. Is it right? Now, to what extent those bodies will appear as separately or distinctly or perfectly, that is called as resolving limit. Okay, so whatever the diagram, I mean, whatever the image we are observing, it should be diffraction free. I mean, we are observing the particles of very, very smaller particles, or not cells, which are very small and comparable with the size of the light. So it will create what, guys? Diffraction pattern. Okay, so here, what is this? Resolving limit. I mean, this diffraction mainly employed or mainly discussed for the purpose of microscopes and telescopes only. What is their purpose? So we will discuss. I mean, first of all, diffraction grating consists of large number of fixed. If light is incident normally on a transmission grating, diffraction principle d sin theta is equal to, okay. See, actually, when the number of glass pieces combined, what will happen, guys? It will reduces the effect. That is only okay. So when equally spaced parallel slits are placed, light incidence on going grating. I mean, some part will it will separate the fringes. I mean, the separate dark ones, dark one, lighter one, it will get separated. That separation is called as diffraction grating. Of course, it is like just an explanation. I mean, what application? We don't have any practical uses. Okay, fine. Now, I already said now resolving power. Resolving power is a very, very important topic with respect to if they ask a question means it is 100% from the resolving power only. Okay, so here the form derivation for the resolving power of a microscope and telescope is also lengthy, and it is not required also. Okay, guys, but I'm going to give you brief idea what is this resolving power of a microscope and telescope. Okay, actually, first of all, resolving power, then of resolving power of microscope or resolving power of a telescope. Okay, so guys, these are direct formula application only. These are direct formula applications only. You need to remember the formula. There's no shortcut here. See, the derivation is a very quite bigger one, and we don't have that also. Okay, so here what is first of all resolving limit. First we will discuss resolving limit. Resolving limit means what, guys? Resolving limit means what? The minimum distance between the two objects to see them distinctly visible. I mean, what is the minimum distance between them? I mean, when we are observing from a longer distance, what is the minimum distance between them to see them as perfectly resolved objects? That is called as resolving limit. Inverse of resolving limit is called as resolving power. Inverse of resolving limit is called as what, guys? Resolving power. So resolving power of an optical instrument is inversely proportional to the wavelength of the light used. Okay, so what is the resolving power of a telescope? Resolving power of a telescope is given as 1 by d theta, which is equal to d by 1.22 lambda, where d is the dia of telescope objective. D is what, guys? Diameter of the objective. Okay, and here wavelength is lambda, which wavelength we have used. Okay, for simple understanding, I'm just explaining here. You can see. Yeah. Okay, guys. So now here, this is the objective lens. Okay. Yeah, it's not good. Okay, this is an object. Okay, it is also not good. Fine. Fine. Okay, this is a objective lens. Now it will cast a image at this point. Is it right? Now here, this is the aperture length. I mean, this is distance. I mean, the total aperture we will call it as what is here total D. Okay. Now here it will subtend an angle. Is it right? Theta. Okay, now here this distance, how much distance it traveled will be 1.22 lambda. Of course, derivation all not required. That's the reason I'm not explaining. Simply resolving of telescope is equal to 1 by d theta is equal to d by 1.22 lambda. Okay, direct. And for a microscope, we are having, for microscope, 1 by d. I mean, d is equal to 1.22 lambda by 2 mu sine theta. But d is what? Resolving limit. Resolving power is equal to 1 by d. Resolving power of microscope is equal to 1 by d, which is equal to 2 mu sine theta by 1.22 lambda, where theta is the angle of the cone. I mean, I already said now how it makes an angle here. Okay, and theta will be given and mu is the refractive index, and lambda is the wavelength used. Okay, so these are the direct formula application oriented only, nothing serious questions or complicated questions. Okay, they won't be asked more than these questions, guys. Okay, hope you all understood about the today's class. Today's class is very simple class. Okay, so first of all, what is diffraction? Bending of light ray into its encroachment or about the corners of an obstacle is called as diffraction, or simply it is the deviation from its rectilinear propagation. We are having two types of we are having how many types, guys? Two types of diffraction. Okay, one is the Fresnel diffraction and one is Fraunhofer diffraction. In Fresnel diffraction, the source and the obstacle are and the screen are at a finite distances from the diffracting devices. Okay, obstacle and screen are at finite distances. It is called as what, guys? Fresnel diffraction. And if the screen and the obstacle are at infinite distances, then it is called as Fraunhofer. In Fresnel, we won't use any convex lenses. Okay, and in Fraunhofer, we will use convex lenses. Okay, so this is the formula. And coming to the next, the width of the central fringe is equal to 2 lambda d by d. Okay, so and the intensity is not the same for all the maximas of those, and the intensity is not same for all the minimas. Okay, these all are the topics here. And path, I mean, in order to obtain condition for obtaining minima is equal to d sin theta is equal to n lambda, and here for maxima is 2n plus 1 lambda by 2. Okay, these all are the topics we discussed. Okay, and the next, diffraction in optical instrument, that only we discussed now. Yeah, so resolving powers. Okay, so these all are the topics, and based on this, the questions are very simple. Directly they will ask the find the resolving power. When resolving power is there, you just need to use the formula 2 mu sin theta by 1.22 lambda. So here, what is this resolving power means? How much effectively it can resolve two bodies, two small particles is there which are closely to each other. Now, how much efficiently it will resolve both those are called as resolving power. Okay, hope you all understood this class. Today's class is a simple and easy. I don't want to make you much burden by taking a lengthy class. I hope you all understood the class. Have a nice day. Take care.